Hi, everyone. I hope that you are having a good first week of the semester. And we are beginning things off this year with our environmental science study. And so environmental science is probably something you know a good bit about, you just may not realize it. And so this corresponds to chapter 9 in our textbook. And I'm just going to do a little mini lecture on this stuff. Again, probably because you know most of this already, and we just need to review. All right, so without energy, all of the tasks that we need are impossible. The fact that you are watching this lecture right now requires energy, right? It requires electrical energy from the device that you're viewing it on. It requires electrical energy from the internet to broadcast the signal to the device you're watching this on. It required electrical energy from my computer to make this video. Everything that we are doing just in this small few minutes that we're spending together here requires energy. It also, if you want to think about it from a biology standpoint, all of the things that we're doing, just to live right now require energy. But we'll get into the biology part later. Right now, we're focusing just on the environment aspects. But right now, where it says residential, you're probably watching this at home. So the residential sector is about 21% of all the total energy that we're talking about in the environmental science section. And so if you want to just see how the United States compares to other countries, here we are and how much we rely on our energy. And so we're not going to get into the nitty gritties of thermodynamics in this class, because this is just a kind of looking at it from 500 feet away. But energy can never be created or destroyed. And that's really the thing that I want you to understand. The energy that we have as electrical energy came from something else. And so I actually have a video here on my YouTube channel that was really recently made. And it's a kid's video, but it demonstrates this idea beautifully that kinetic energy, which is the energy of motion, can be used to turn a turbine, which is a spinning wheel that connects to a generator, which creates electrical energy, which is then sent out. And so all energy, whether it's kinetic energy, potential energy, electrical energy, all energy must be transferred from one source to another. It's never created, it's never destroyed. And I'll put a link to that little video, little kiddie video, but it demonstrates it beautifully, and it's like a 1.5-minute video. So you should definitely check it out. The second law of thermodynamics is not something you're going to be tested on in an exam, but I just kind of wanted to throw it in here in case you see it again in the future. It's that for things that happen without help, in other words, spontaneous things, the whole system becomes more disordered. And what that means is, think about your car, or my car. If you are eating your lunch in your car, which takes more effort, to just throw your trash on the floor and say, well, see you later, or to collect up all your trash and take it out of your car with you? If your car looks like my car, it's a mess, right? It's way less energy to just throw it on the floor. That is more disordered. And so the easier route is for things to become more disordered. And when we're talking about producing energy, that is the opposite of that. You're actually making things more ordered. And so this is why effort is required when we're talking about producing electricity or any of the energies that we're using right now to power our electrical devices. I didn't mean to have that in there, so let's just get that out real quick. Delete. All right. So here in the United States, if you want to look at which kinds of energy sources we use, we've got biomass down here. Look, that's kind of the lowest. We've got coal, we've got petroleum, we've got natural gas, we've got nuclear. All of these guys all operate on the exact same principle. And it's really interesting to think about this. I actually used to teach middle school at one point in my career, and my students and I actually made kind of models of all of these. And the interesting thing is that they all end with the exact same result. So if you, for instance, burn coal, okay, you burn your coal, the burning coal creates heat that's used to boil water. That boiling water makes steam. The steam turns a turbine, which turns a generator, which kicks out your electricity. If you're burning petroleum, guess what the only difference is? What you're using, right? If you burn petroleum, the petroleum makes heat. The heat boils water. The water makes the boiling water steam, turns a turbine, which turns a generator, which makes your electricity. If you're burning natural gas, you burn the natural gas, that creates heat. Heat heats the water. Water makes steam. Steam turns the turbine. Turbine turns the generator. Out comes your electricity. If you're doing a nuclear reaction that creates heat, what does the heat do? Heat boils water. Water makes steam. Steam turns the turbine. Turbine turns the generator. Out comes your electricity, right? So all of these are basically the exact same process of making electricity. The only difference is, what are you burning? Are you burning coal? Are you burning petroleum? Are you burning natural gas? Are you performing a nuclear reaction? For hydroelectric works the exact same way, except instead of burning, you just have falling water, turns the turbine, turns the generator, kicks out your electricity. But the point being here is these guys are all very similar in that you have to have a turbine, which turns a generator, which kicks out your electrical energy that we're using to power our lights right now. And so here in the United States, if you want to kind of get freaked out, how many years do you have until these sources are depleted? Well, you can check this out. And here are the sources that they came from. And this figure's from your textbook in chapter 9. So fossil fuels are your natural gases, your petroleums, your coal. And we're going to talk more about the chemical structure of what a fossil fuel entails a little bit later in the semester. And so where the fossil fuels came from, well, they came from ancient plants, right? Photosynthesis created these molecules. And when we combust them, burn them, we're just taking this reaction and going the other way. So this is what I was talking about just a minute ago. Oops. Where I said you burn it, creates heat boils water, water turns the turbine, turns the generator, gives you your electricity. Here's just a picture of that exact same thing. So you're burning your coal, that's all your waste coming out right here. The heat boils the water, which then makes steam. The steam goes into the turbine. The turbine turns a generator, which makes your electricity. And this is what I was talking about just a minute ago, whether you're doing coal burning here or petroleum burning here or natural gas burning here, all works the exact same way. You could literally pick up this piece and just plop it into the other source. And if you're talking about hydroelectric water falls, and that's what turns the turbine and the generator. And if you're talking about nuclear, you've got some sort of nuclear reaction happening here that's creating your heat. So all of these processes are very similar. They all end the same way with some generator turning and kicks out your electricity. So smog is something that we have to worry about when we talk about energy production, electrical production, right? Because if you did perfect combustion of hydrocarbon is this molecule containing only carbon, hydrogen, and oxygen. If this reaction goes perfectly, you should only get H2O and CO2. But because we're talking about fuels here, you're going to have impurities. And those other products are the problems that we then have to deal with, such as carbon monoxide, right? Carbon monoxide is a poisonous gas. I really hope you have a carbon monoxide detector in your home if you have a furnace, because if your furnace is burning and you get some of that carbon monoxide kicking out and it's getting into your home, that's poisonous. So make sure you check if you have a carbon monoxide detector. You also have nitrogen monoxide, poisonous, and if you're breathing it straight up, right? And it's not something that you want to be hanging out with. Ozone, all of these are byproducts that result from incomplete combustion. And when you're dealing with coal and petroleum and natural gas, you're going to have that stuff. So in your car, you may or may not know this, but in your car, you've got this thing called a catalytic converter, and its goal is to decompose nitrogen monoxide. So here's your engine over here, and here are the gases coming out of the engine, and inside the catalytic converter, you're decomposing those undesirable gases so that what's coming out is not nitrogen monoxide. All right, something else you may have heard of before, acid rain. This is when fossil fuels give us sulfur dioxide, SO2. And again, this is all coming from impurities, right? If you were burning a pure hydrocarbon, you wouldn't get these impurities. You would only get H2O and CO2. But because we're dealing with fossil fuels, you're going to have impurities, nitrogen impurities, sulfur impurities. And so you have to deal with the fact that you're going to get SO2, you're going to get nitrogen monoxide and nitrogen dioxide. These guys all are present when you burn a fossil fuel. And obviously that gives us this problem that we have to deal with as acid rain. So we get these gases kicked out during combustion. And here's a nice little figure, right? These gases come out of the tower, byproducts. Okay, the wind takes it up to the atmosphere. It combines in the clouds. It's part of the clouds now. And then as the water is coming down, it's taking this with it. This dissolves in the water. It gives you an acidic rain, which is obviously not good for the wildlife, not good for you, not good for the buildings, not good for really anybody. So this is one of the problems and the downfalls that you have when you're talking about burning fossil fuels. And then the other big piece that I'm sure you're familiar with is called global warming. And this is an increase of the global temperature. So here's a nice little picture worth 1,000 words, right? A greenhouse, this is what a greenhouse is. It's this little building and it's designed so that when the sun's heat comes in, the heat stays in, it helps plants grow so that in January, your plants are still living. Well, that's what a greenhouse is. So the greenhouse effect is kind of the same premise, except instead of being this lovely little greenhouse, it's now our planet. And these gases are acting like the glass panes of the greenhouse. When the sun shines in, the heat stays inside. And so this figure's from your textbook, just showing how the average global temperature has changed since approximately 1880. And here's another figure from your textbook looking at samples of ice from ice core, right? So we're talking about ancient ice, old ice, and how it's changed over time. And then again, this is just looking at it over time. So in summary, this is the part of the environmental science section of chapter 9. The main idea from a molecule standpoint is that energy is the transfer of energy, and that when we burn a fossil fuel during combustion, we're going to get both the products that we're interested in, i.e. the heat and the energy, but we're also going to have these side products that we have to deal with. So energy is important. It's a component of our daily lives. You wouldn't be able to do what you're doing right now without electrical energy. However, the downside is we have to figure out what can we do to make our health optimized in these conditions, right? So again, this is just a review of some things that you're already familiar with. And if you have questions, please don't hesitate to to call me or email me. Thanks. Bye.